dealing with a wave mechanical picture of scattering, which leads to the scattering amplitude. As in my previous video, we had discussed about the scattering process, the mechanism of scattering process. There we had told about the particles, uninterrupted beam of particles which are incident onto the target. Here the particles that are involved in scattering process are quantum mechanical in nature. Then we have to describe them by wave function. This wave function will be a stationary one. As we had previously told, there is a steady incident beam of particles which is maintained at all times. Thus, we consider that the wave function will be a stationary one. Now, the phenomenon of scattering is manifested as a distortion in the stationary wave pattern. So, you can see that we have a stationary wave pattern, that is, we have a continuous beam of particles incident onto this target. Okay, and after hitting onto this target, what happens to the stationary wave function? It gets distorted. So that is the basic phenomenon which we are considering in the quantum mechanical picture. So now at large distances, what happens? Now you have the incident wave, plane waves hitting onto the target. So at large distances, suppose we say at infinity, you can see that there will be incident particles, okay, plus you can see that there will be scattered particles. There will be particles which comes just without touching the target, and also after getting scattered by the target, which we have called it as a scattering center. So this is a basic phenomenon which we are going to develop in the quantum mechanical picture. Okay, so we assume that the incident wave function as psi incident. Okay, it is psi incident, and the scattered as psi scattered. So now at large distances, what we assumed is psi of x will be of sum of psi incident plus psi scattered. Now we have to find out the scattering cross section in terms of the asymptotic wave functions. So we assume that the incident particle has a momentum P is equal to h cross k along the z axis. So I would like to again remind that we will be considering the polar coordinates, that is the incident direction as z axis, and we have the scattering angle theta and the azimuthal angle phi. So here we have considered the momentum h cross k, which is along the z direction, and this must evidently be described by a plane wave, that is psi incident we consider as a plane wave, and a plane wave can be represented as e raised to I kz. Okay, and again we know that this wave function modulus square is to be understood as the number of particles per unit volume. So this must be the number of particles per unit volume. Now we want to find the flux, incident flux, and we give it as the letter capital F. It is obtained by multiplying the number of particles per unit volume times the velocity of the particle that we had seen earlier in our scattering process. So this times V. Okay. Now what is your V? In terms of momentum, we know that P is equal to M into V. And P is nothing but H cross K divided by M will be equal to your V. So we can substitute that here and we'll get it as this modulus incidence square. We can put it as 1 because we have the probability as 1. Then or you can just tell this, no, what is this? E raised to I k z modulus square. It is equal to 1. Okay. So what we have is H cross K by M. Okay. So let's put it as equation number. This we'll put it as equation number 1 and this as equation number 2. F is equal to H cross K by M. Now this is about the incident particles. So again I repeat, the incident particle we consider as a plane wave. Psi incident is equal to, and that a plane wave can be represented as e raised to I kz. Okay. And now we have to find out the flux. Flux is nothing but the number of particles per unit volume. And what is that? It is modulus of psi incident square times the velocity. So you know the number of particles hitting per unit time, that is their flux. Per unit area, per unit time is the flux. So it also depends. If the velocity is low, the flux also will be smaller, and if it is high, it will be same. So it is dependent on the velocity. So we have F is equal to H cross K by M. Now we will be speaking about the scattered particles. And we consider that scattering is elastic. The wave function psi scattered also has the propagation, since it is elastic, it has the propagation constant K. And we know that in the previous talk we had told that it is spherical in shape. No, it will hit the target, and then you should get reminded about that. We have considered a cone-like structure. So we can say that it is a spherical wave. Okay, here it is a plane wave. In this case, it is a plane wave. Psi scattered is a spherical wave, which means that it is moving radially outwards. Then these spherical waves, we know that it is represented by e raised to ikr and also e raised to minus ikr. So here e raised to ikr is the outgoing wave and e raised to minus ikr is the incoming wave. And we know that the scattering is always outwards. Therefore, psi scattered can be represented as, is proportional to e raised to I kr. Okay. Again, you know, as distances increases, what happens? The scattering particles also decreases, and that we can give it by R. So it is inversely proportional to R. This psi scattered now can be replaced by some constant. We call it f theta phi. Okay. E raised to I kr by R. So this is my equation number 3. Again, we observe that the number of particles, that is delta n, is nothing but the radial flux times, that is delta s into dt. Okay, is equal to delta s into dt. Now what is a delta s? It is nothing but r square d omega, okay, into dt. Therefore, we can say that number of particles delta n into a small solid angle d omega can be written as modulus of psi scattered square into that velocity. Now you know how velocity can be represented, no? We have written that here, h cross k by m, h cross k by m into r square d omega dt. And we know that psi scattered square is this one. We can write it as modulus of f theta phi the whole square h cross k by m, that's your velocity, times d omega dt. If you put this as v, it is alright, because you can write this as again v itself, modulus of f theta phi the whole square v into d omega dt. That's my delta n. So this I'll give it as equation number 4. Now comparing equation 4 with this, okay, d sigma by d omega dt into f. You know what flux is now, no? We have written flux as equal to here. Now where is my flux? As is equal to h cross k by m, okay. So you can see this is this you can write this as a flux also, f h cross k by m. Now you can compare it with your equation number, in the previous section we have given us equation number 1, okay. So this equation, I'll just take it out. So I'll just keep it here. So this is my delta n. Delta n is, which I have got it in my previous lecture notes, just the first part of it. So this is my first equation. So when I compare this with this equation, you can see that this is flux. H cross k by m, we have taken it as the flux here, the second equation, according to second equation. Okay, I can put it as h cross k by m. So this equation would represent modulus of f theta phi the whole square f d omega dt. So when comparing equation 4 with 1, we can see that d sigma by d omega is equal to modulus of f of theta phi the whole square. Okay, this is a very important result. It is a relation between f theta phi modulus square and the absorption cross section. So f theta phi is called the scattering amplitude. Okay, so always you will be asked the question, what is called the scattering amplitude? So you can represent this in terms of your absorption cross section or the scattering cross section. So you can, it's better to tell it as a scattering cross section, sorry. So now what is your equation? We have written that in equation 1 here we have written psi of x is equal to psi incident plus psi scattered. Psi incident, you know, it is e raised to I kz, the plane wave, and psi scattered you have got it as f theta phi e raised to I kr by r as equation 3. Okay. So we can write psi of x is equal to e raised to I kz plus f theta phi e raised to I kr by r. Okay. So we have a condition, no? So it is R asymptotic solution, asymptotic region meter, that is R tending to infinity. Okay. So at R tending to infinity, your function, wave function would look like e raised to I kz plus f theta phi e raised to I kr by r. Since this stationary wave function, this I'll put it as equation number 6. Since this stationary wave function must satisfy the time independent Schrodinger equation, we have minus h cross square by 2m del square psi of x plus v of x psi of x is equal to E psi of x, and you know that E is nothing but is equal to h cross square p square by 2m, no? So it is h cross square k square by 2m, and V of x is nothing but your potential energy function for the projectile particle in the force field of the scattering center. So this is what the relation I would like to tell about the relation between the scattering amplitude and the scattering cross section.